Welcome to our 2025 to 2026 survey of bimanual manipulation foundation models. Today we're covering 5 landmark systems, p0.5, GR00T N1, UniDex, DualCoT-VLA, and VTAM, that are reshaping what robots can do with 2 hands. Let's start with the landscape. The bimanual manipulation field has undergone 3 distinct eras in just 3 years, from narrow task-specific scripts all the way to open-world foundation models. Before 2023, the dominant approach was task-specific learning. Systems like ACT and diffusion policy trained 1 skill per task, great performance in the lab, but completely brittle to any scene or object variation, and 0 language understanding. Then in 2023 and 2024, the VLA era began. OpenVLA, the original Pi0, and RT2 all fused vision, language, and action into a single model. Multitask generalization became real, but these systems were still constrained to controlled lab environments. The core challenge is that bimanual manipulation is genuinely hard. You need 2 arms to coordinate in real time, generalize across wildly different objects, work around severe data scarcity, and bridge the embodiment gap between robot models with different morphologies. Let's go deep on Pi0, the architecture that started the foundation model era for bimanual robots. Built by Physical Intelligence in 2024, it combines a large vision language model with a novel flow matching action head. The inputs are multi-camera RGB images, a natural language command, and the robot's current joint states. This multimodal input is what allows the model to understand both the visual scene and the goal simultaneously. Those inputs feed into PaliGemma, a 3 billion parameter vision language model pre-trained on internet scale data. This is where Pi0 gets its scene understanding and language grounding. The VLM backbone is frozen from pre-training and then co-trained with the robot data. The key innovation is the flow matching action head. Unlike diffusion, flow matching generates smooth continuous trajectories much faster. It learns to map Gaussian noise directly to action chunks, giving you precise, fluid arm motions at 50 Hz. The results are impressive. Pi0 handles laundry, dishes, wiping, and packing long multi-step tasks that require both arms and precise force control. It outperforms prior VLAs by a large margin on bimanual benchmarks. Pi0.5 is the follow-up from Physical Intelligence in 2025. The question they asked, can a robot generalize to a home it has never seen before? The answer required 1 key architectural addition. The big addition is a high-level task planner. Before the robot takes any action, this planner decomposes the language goal, clean up the kitchen, into concrete subtasks. This 2-level architecture separates what to do from how to move. The demo tasks run in real homes, loading the dishwasher, folding laundry, cleaning the sink, organizing drawers, packing bags, kitchen prep. These are not scripted environments. The robot walks into a stranger's kitchen and gets to work. The numbers, roughly 65% success on unseen homes, compared to around 25% for the base Pi0 without the planner. Multi-step tasks with 5 to 10 subtasks completed end-to-end. This is the clearest demonstration yet of open-world household robotics. NVIDIA's GR00T N1 takes a different angle. It's designed for humanoid robots, full-body coordination, not just arm manipulation, and its open weights, which is unusual for NVIDIA. Inputs follow a similar pattern: camera feeds, a language command, and the robot's full body state including both arms and legs. The key difference is the downstream architecture. GR00T N1 uses a dual system design inspired by cognitive science. System 2 is a slow VLM that handles reasoning and planning, figure out what to do. System 1 is a fast action model for real-time motor control, figure out how to move. They run at different frequencies. The secret weapon is Omniverse. NVIDIA generates millions of synthetic robot demonstrations in Isaac Sim using domain randomization across lighting, textures, and object poses. This eliminates the expensive teleoperation bottleneck and enables sim-to-real transfer at scale. Crucially, GR00T N1 is released as open weights and designed to work across multiple humanoid platforms, Unitree H1, Figure 01, and custom embodiments. This cross-platform openness is genuinely rare in the industry. UniDex from NVIDIA attacks the data problem head-on. The insight: we don't need robot teleoperation demos if we can learn from human hand videos, which exist in the billions on YouTube and social media. The pipeline starts with egocentric human hand videos at web scale. These are first-person views of people doing everyday manipulation, cooking, crafting, using tools. No robot required to collect this data. Why does this matter so much? Data scarcity is the single biggest bottleneck for dexterous manipulation. UniDex's approach unlocks billions of free demonstrations. The field has been stuck waiting for expensive robot teleoperation. This changes the economics entirely. The resulting policy handles impressive dexterous skills, in-hand rotation, pen spinning, card manipulation, precise insertion tasks, and deformable object handling across shadow hand, Allegro, custom grippers, and bimanual setups. One policy, any hand. DualCoT-VLA from AR14 March 2026 asks, what if we gave the model explicit reasoning steps before it acts? Chain of thought has transformed LLM capabilities. Can it do the same for robot control? The key innovation is running two separate COT streams in parallel. The visual COT handles perception, object detection, spatial reasoning, scene parsing. The language COT handles planning, task decomposition, step sequencing, constraint checking. Running them in parallel keeps latency low. The dual-stream approach handles much longer task horizons, 7 to 12 subtasks, compared to single COT baselines. The model also recovers better from mid-task failures because it can re-reason about the current state rather than blindly continuing. The numbers: plus 24% task completion over standard VLA baselines. Tested on peg insertion, assembly, cloth folding, and pouring tasks. This is a clean demonstration that explicit reasoning before acting is worth the architectural complexity. VTAM, the Video Tactile Action Model from AR14 March 2026, tackles a fundamental limitation of every other model we've covered: they're all blind to touch. For deformable objects, vision alone is simply not enough. Here's why touch matters. When you're folding cloth, routing a cable, or kneading dough, the crucial information is haptic, force magnitude, slip detection, contact area. Vision can't tell you if your grip is about to fail. VTAM is the first VLA class model to fuse both modalities. The video and tactile streams are fused into a joint world model that learns implicit predictions of object state over time. It learns when to grasp harder versus lighter, and it can predict task completion likelihood, essentially a continuous self-evaluation signal. The capabilities unlocked are remarkable: cable routing, dough kneading, cloth spreading, tasks that completely defeat all prior VLAs due to deformability. VTAM outperforms RGB-only models by 2 to 3 times on deformable object benchmarks. Let's bring it all together with a direct comparison. 5 models, each with a distinct strength, and each with a real limitation that reveals where the field still needs to go. π0 and π0.5 from Physical Intelligence are the open-world leaders. Real homes, unseen environments, multi-step tasks. The limitation: fully proprietary, closed hardware, closed data, closed weights. You can read the paper but you can't build on it. GR00T N1 is the open humanoid champion. The dual system architecture plus Omniverse synthetic data gives it massive scale. Open weights, multiple platforms. The trade-off: it's primarily humanoid focused, so adapting it to non-humanoid robots takes work. UniDex is the data efficiency breakthrough. Open dataset, open weights, cross-embodiment policy. But it's a dexterous hand model, no full body coordination, no locomotion. It's the piece that plugs into a larger system. DualCoT-VLA proves that explicit reasoning lifts task completion by 24%. The cost is inference latency: 2 parallel reasoning chains take longer than a direct policy. For time-critical tasks this matters. For household chores, it doesn't. The 2026 Convergence Thesis: the next breakthrough will combine all of these: reasoning from DualCoT, tactile sensing from VTAM, cross-embodiment openness from UniDex, and synthetic data scale from GR00T. The open problems are sinterial latency, safety guarantees, and natural human-robot handover. Watch for Pi1, GR00T N2, and tactile language models in the months ahead.